Let's consider the phase equilibrium between two phases of a simple one-component system. Suppose in a condition on the phase boundary, A, the molar Gibbs free energies of phase 1 and phase 2 are G1 and G2, respectively. G1 is equal to G2 because the two phases are in equilibrium. In another condition, B, which is also on the phase boundary and is close to A, the molar Gibbs free energies of two phases are also equal. In the condition B, the molar Gibbs free energy of phase 1 is G1 plus dG1. The molar Gibbs free energy of phase 2 is G2 plus dG2. Thus, dG1 is equal to dG2. Then, we use the infinitesimal change of Gibbs free energy. Pay attention, the molar volumes of the two phases are different. The difference in the molar volumes of the two phases in equilibrium is the volume of phase transition. The molar entropies of the two phases are also different. The difference in the molar entropies of the two phases in equilibrium is the entropy of phase transition. Then, we can express the ratio between dP and dt. It is so-called Clausius-Clapeyron relation. dP over dt is the slope of the tangent to the phase boundary in the temperature-pressure phase diagram. The entropy of phase transition at constant pressure can be replaced by the latent heat or enthalpy of phase transition divided by temperature. We can use Clausius-Clapeyron relation to explain many phenomena in phase transitions. Let's have a look at fusion first. The temperature at which the solid phase and liquid phases are in equilibrium is called the melting point or freezing point. The volume of fusion is much smaller than other phase transitions because both liquid and solid are already condensed. Thus, the absolute value of the slope of the tangent to the phase boundary between the solid and liquid phases is the largest. The enthalpy of fusion is always positive. The volume of fusion is usually positive as well. So, for most substances, the melting point raises slowly with pressure. Carbon dioxide is an example of this type. Please pause the video here to check the example by yourself. However, water is an exception. Near standard pressure, the density of normal solid ice is lower than liquid water. Thus, the molar volume decreases during the fusion of ice. The slope of the tangent to the phase boundary between the solid and liquid phase is negative. That is, the melting point of ice lowers with pressure. Then let's consider the phase transitions involving a vapor. A vapor is a phase which can be condensed or deposited by increasing the pressure on it without changing the temperature. In other words, a condensed phase can be vaporized or sublimate by increasing the pressure on it without changing the temperature. The pressure on the vapor-condensed phase boundary is its vapor pressure. For a liquid, if its vapor pressure is greater than the pressure of the surroundings, the liquid vaporizes spontaneously. It is because, by releasing to the surroundings, the pressure of the vapor decreases, so its Gibbs free energy decreases. Boiling is the rapid vaporization of a liquid. The boiling point of a liquid is the temperature when its vapor pressure is equal to the surrounding pressure. On the phase boundary, the degree of freedom is 1. Thus, vapor pressure depends on temperature. For example, when the temperature is 100 degrees Celsius, the vapor pressure of water is 1 bar. The vapor pressure increases with temperature. On the other hand, the boiling point depends on the surroundings pressure as well. The boiling point of water at 1 bar is 100 degrees Celsius. The boiling point raises with the surroundings pressure. In fusion and sublimation, the volume of the vapor is much greater than that of the condensed phases. Therefore, the volume change is approximately the volume of the vapor. Furthermore, in most conditions, the properties of the vapor are close to that of ideal gas. Thus, the volume of the vapor can be replaced by pressure and volume according to the ideal gas law. Insert the expression of volume to the Clausius-Clapeyron relation. The resultant equation is a typical ordinary differential equation. It can be solved by the separation of variables. Move the pressure to the left side and the temperatures the right side of the equation. Integrate the equation from the initial to the final state. We further assume that the latent heat is nearly independent of temperature. Then, the integral is simplified to the so-called Clausius-Clapeyron equation. This equation describes the relationship between vapor pressure and temperature. Here, I show you the temperature versus vapor pressure plot with experimental results and calculation by Clausius-Clapeyron equation. You can see that Clausius-Clapeyron equation reproduces the experimental result pretty well at high temperature because the normal boiling point is used as the reference. At low temperature, the discrepancy between experimental result and our calculation by Clausius-Clapeyron equation is mainly caused by the difference in the heat capacities between liquid water and water vapor, which leads to a temperature-dependent latent heat. Clausius-Clapeyron equation explains why cooking is difficult on plateau. As altitude increases, the atmosphere pressure decreases. For example, at sea level, the atmosphere pressure is 101,325 Pascal. The boiling point is 100 degrees Celsius. At an altitude of 4,000 meters above sea level, the atmosphere pressure reduces to 61,617 Pascal. The boiling point of water lowers to 86 degrees Celsius. That is, the cooking temperature is limited to 86 degrees Celsius. Cooking is essentially a series of chemical reactions. A low cooking temperature lowers the rates of them. On the other hand, a pressure cooker can bear a pressure higher than the atmosphere pressure. So, the boiling point is raised. For example, if a pressure cooker cooks at a pressure of 2 bar, the boiling point of water raises to 120 degrees Celsius. Such high temperature accelerate the cooking significantly.